Alright, so the exactly 0 people who ever pay attention to anything I say will have seen this coming. But I have finally come around to accept some conclusions of some predictions of what I've been saying for a couple of years now. And I have a resolution to the continuum hypothesis. Right. Basically, it results from Hilbert's axioms just being a fucking disaster in the first place. Okay, so the continuum hypothesis is independent of Zermelo-Fraenkel set theory, with or without the axiom of choice, because of Cantor's assertion that the cardinality of integers is smaller than the cardinality of reals. Fundamentally, what's going on here is we're talking about the size of sets without any way to actually measure these sizes. Set theory can't handle that. Okay, and Cantor's argument is based on the Archimedean property, which at first blush seems totally reasonable. And this renders the bijection between the integers and reals impossible. You cannot then map the integers to the reals, right? If the Archimedean property holds 100%. And you might notice that the Archimedean property is among Hilbert's axioms, which was published in 1899. And the first of Hilbert's 23 problems, which was published in 1900, 1 year later, not even really, is whether or not the continuum hypothesis can be shown to be true or false. Okay? Now, if we're paying attention to anything, it's trivial to show that the Archimedean property in fact does not apply to cardinalities of infinities. And I think this is related to why Georg Cantor was actually talking about transfinites for the most part. Yeah, I'm not entirely sure what happened with Cantor's work, but from what I can see, he kind of just slightly overstepped, and then everyone just took that and ran with it. So Georg Cantor was wrong to assert that the integers have a different cardinality from the reals based on the Archimedean property, right? And this can be seen, for instance, by considering the behavior of y is 1 on x in the neighborhood of 0, right? At x equals 0, we have no y value at all. But immediately to the right of x equals 0, the y value is positive infinity. And immediately to the left of x equals 0, the y value is negative infinity. So you move the tiniest possible amount in either direction, and your result changes completely. And what you get when you move the tiniest amount, the tiniest possible amount, an atomic amount, is you get not just infinity, not just a value that you cannot reach arithmetically, but what you get is the infinity. You get the attractor to infinity, okay? Positive or negative. So it has some numerical properties. It has, well, has some vector properties, right? Which is, normally we consider the things we call numbers are vectors, so it sort of holds. Yeah, they can have signs, right? They can be positive, negative, imaginary, whatever, right? Now, these infinite y values are not subject to manipulation via arithmetic because they are not ordinals, right? And as such, the Archimedean property cannot apply to them. This means that 0 has discrete immediate neighbors on either side. There is an immediate neighbor to 0 on the positive side, whose inverse is positive infinity. If you go twice that far, you're now at a transfinite value. Right? It behaves very much like an infinity, but it's transfinite. It is no longer infinite. Okay. Now, this means that it becomes possible to establish a bijection between the integers and the reals. which then resolves the continuum hypothesis by demonstrating that not only is there no cardinality between that of the integers and the reals, but that the cardinality of the integers is the same as the cardinality of the reals. Right? And to be clear, the moment that I realized that L naught exists, L naught being my name for this value immediately to the right of 0, because if you want the negative of it, you just take negative L naught if you want. Right? If you want the value immediately to the right of pi, you just say pi plus L naught. Or it could be L of pi. It doesn't matter. Either way you construe it, it's the same thing. The moment I realized that this exists, I noticed this, but I'd been assuming that there was something that I was missing, something I'd done wrong, and thus that this was an incorrect prediction. But after mulling it over for a few years and looking at the reason for the conventional claims, I've grown pretty confident that it's not a mistake on my part, and it's a mistake on the part of others. It looks fundamentally like the problem was acceptance of the Archimedean property, just blind acceptance of that. That really seems to be pretty much the exclusive source of this issue. But also regarding Hilbert's axioms, the interpretation of Euclid's fifth postulate, which appears in Hilbert's axioms, it just doesn't make sense, right? It's alleged to be equivalent, but it isn't, right? So Euclid's version specifies straight lines of infinite extension, okay? When this is factored in, it becomes impossible to apply the fifth postulate to curved spaces, like spheres. For instance, on a sphere, every straight path falls on a great circle, which by definition does not have infinite extension because it's a circle. It comes back around to itself. It has a set perimeter length. Further, these paths can only be considered parallel to each other at two specific points. If you have two great circles, two distinct great circles, there's only 2 points at which you can consider them to be parallel, since at all others they're converging towards each other or intersecting. But you can get paths on a sphere that don't intersect, so perhaps it's fair to say that the fifth postulate applies to them? Well, no, because again they're still circles, and thus do not have infinite extension, but also because they're not great circles, they're curved paths on the surface of the sphere. Right, so a beautiful example of this would be lines of latitude. Right? A line of latitude, if you want to follow a line of latitude that is not the equator, any other line of latitude, you have to be constantly turning slightly. Right? As you get really close to, say, the North Pole, this becomes very, very obvious that you have to be constantly turning. You can actually see it on the ground. You can measure it very obviously. But, when you're down, in the lower 48 states, somewhere like Australia or most of Africa, really anywhere in Africa, South America, right, inhabited places, it's less obvious, but it is definitely the truth that in order to follow a line of latitude, you have to turn, unless that line of latitude is the equator, in which case it is a great circle. Right? And this is just a property of the surface of the sphere. Alright, and that means that you cannot be considering these straight lines. So, we're not following Euclid's fifth postulate here. Now, Hilbert's interpretation of Euclid's fifth postulate, quote-unquote, solves all of these concerns by simply removing the specifications for straightness and infinite extension, which, one should note, makes Hilbert's form entirely distinct from Euclid's, contrary to the claim that they're equivalent. And now, to be clear, this is by no means uniquely David Hilbert's fault. The tradition of using incomplete variations of Euclid's fifth postulate goes back at least to Proclus. and was in a quite developed state by the time Hilbert was born. However, you'd think that someone at some point would bother to actually compare the folk traditional claim that is established to what Euclid's fifth postulate is against the actual text in the Elements, because we do have that. You can just read what Euclid said. Interestingly, Augustus de Morgan argued that using Euclid's definition of parallelism obviated any need to use the fifth postulate at all. And since the fifth postulate is said to be violated by non-Euclidean geometries, where in truth it simply can't be applied for a number of reasons, including those noted for spherical geometry, he felt it was okay to just ignore it altogether, more or less. I'm very much simplifying this, but that's the gist of what happened. And this fed into the mathematical culture of the time, which was obsessed with reinventing everything and finding broader, more generalized ways of saying things that would apply to more use cases. Superficially, that seems like what you would want to do. But the trouble with that is that when you try to make a single tool that's a hammer, a plane, a vise, and a wrench all in one, it's gonna suck at all of those tasks more than purpose-built tools, right? And that's precisely what we got from this late 19th through mid-20th century revolution in mathematics. More generalized tools that simply suck at doing anything. And specifically, to take this analogy a little bit further, like, in order to use a hammer, right, the weight of it, the distribution of the weight, it's all important. But if you start trying to, like, drop other tools on it in different places, you're going to throw the weight off. So it's not going to work quite as well. So things that you might just assume from how you would use a hammer, right, like the swing and how much effort it takes, and so thus how many nails you can drive in an hour or in a day of working, that's now going to change. But if you're operating from the assumption that this is how hammers work, instead of this is a consequence of the way this hammer is built, you're not going to reanalyze what you can do with the hammer after you make the changes. And that's precisely the sort of thing that occurred here. Because you have figures like De Morgan coming in and saying that these things are logically equivalent, more or less what occurred is the way stuff worked before was just assumed to carry over without any impact after changes were made. And that doesn't work. That's not how anything works. You make changes, and you change how stuff works. That's what a change is, right? So it impacted all of this, and so Hilbert's program pretty much failing is, I would argue, primarily related to Hilbert's questions, Hilbert's 23 problems, however you want to phrase that, being unsound questions in the first place. Because what happened is we made too many changes too quickly without anybody really critically looking at the consequences of those changes. And the mathematical community just tried to run with it. All right. And the continuum hypothesis is among these. It's part of this period of this rapid change where just not enough eyes were paying attention to, not enough eyes were on the problem. So not enough people were able to pay attention to the changes that were occurring, and people got wrapped up, probably, speculation, but probably they got wrapped up in their own egos, and they're like, okay, yeah, we've solved this, we don't need to work at that anymore, we can just assume this. I've seen this working in other branches of science. particularly in linguistics, where I spent a lot of time. I've seen this specific thing happen where people are just unwilling to ever go back and reassess things that were established prior because it's just part of their dogma, frankly. And so, it's what they were taught. It's so it has to be true. It carries forward, and the changes that they make in the system can't apply to that because those things are foundational. Those things are basic, and it becomes this war with their ego versus reality. I've seen this, and so I imagine this probably is at least part of what's happening here too, especially since we know we have figures like David Hilbert and Bertrand Russell who have very big egos. We know this. It's documented very, very clearly. So, this is an overview of, at this point, what I think is going on here. And I think, fundamentally, the continuum hypothesis is a malformed question. Asking, is there cardinality between that of the integers and the reals, right, between Aleph naught and Aleph 1? It's malformed because you're assuming something that you can show doesn't actually occur. Right? You're taking as an axiom the Archimedean property because working from an arithmetic or a geometric point of view, generally, casually, right, like a Greek geometry sort of point of view, you're never able to establish an atomic, discrete division of the continuous space. But that doesn't mean that you can't do it. That only means that you can't do it via something that's commensurable with arithmetic, like classical geometry. But you can show, simply by looking at inverses, functions of, or a function that's an inverse, right? Like y equals 1 on x, or y equals tangent of x. Something like that, where you end up with these inverse relationships occurring. When you get those, you can see it. That there has to be, actually must be, it's inescapable, a discrete value on either side of 0. That is the immediate neighbor of 0. And what this is the ideal limit as we approach 0. 0 itself is not the ideal limit, but the value right next to it is. Just immediately next to it. And in these situations where we're running into problems, usually what's happening is the inverse of that, we're dealing with the inverse of that value directly, which is infinite, which is not an ordinal, so it does not cooperate with arithmetic. And this is where we get problems with singularities and other things. And again, it is more nuanced than what I'm saying right here, but this is kind of the gist of it, right? Yeah. And somehow that hasn't really been appreciated yet. Yeah, there's a lot more to this, but yeah, that's kind of the gist of it. So the continuum hypothesis, I think, is a malformed question, because what ends up happening is, if you accept the idea of bijections, which I really don't personally, but if you do, and you are able to get this discrete neighbor to 0, what now happens is you can now establish a bijection between the integers and the reals, all reals, and they are now exactly the same size. And we've dissolved the continuum hypothesis, because now there's not anything between the cardinalities of the integers and the reals, because they are identical to each other. And they're like LF2 and LF1 are the same thing also, which is currently unknown as well, whether they're the same or not. But under this view, they are now the same as each other as well. And all cardinalities of infinite sets are identical now. There is only one infinity. And, importantly, this does not actually induce any losses. What it does is it resolves paradoxes. That's all it does.